In this video, let us understand the definitions of AI, ML, TL, and generative AI with practical examples. Artificial intelligence is a broad field that focuses on building systems capable of performing tasks that would normally require human intelligence. These tasks include understanding speech, making decisions, and adapting to new information. In our everyday lives, AI appears in many familiar forms. For example, virtual assistants like Siri, Alexa, and Google Assistant can understand what we say, answer our questions, and control our smart devices. In the financial sector, fraud detection systems uses AI to identify suspicious activities and prevent fraudulent transactions, protecting both banks and customers. And in the transportation, traffic navigation apps such as Google Maps use AI to analyze real-time traffic data and dynamically suggest the fastest routes to your destination. Machine learning is a branch of artificial intelligence that enables systems to learn patterns from data and make predictions or decisions without the need for explicitly coding every possible rule. One everyday example is email spam filters. These systems learn from large set of labeled messages, identifying which ones are spam and which are legitimate, so they can automatically filter your inbox. Another example is product recommendation systems used by platforms like Amazon and Netflix, which analyze your browsing and purchase history to suggest relevant products or shows. In finance, credit scoring uses machine learning models to evaluate loan eligibility by examining your financial history and identifying risk pattern. Deep learning is a specialized subset of machine learning that uses multi-layered neural networks, often called deep neural networks, to process and learn from massive amounts of data. These networks automatically discover complex patterns, making them ideal for highly sophisticated tasks. For example, facial recognition on smartphones uses deep learning to analyze and match unique facial features, allowing secure device unlocking. In the automotive world, self-driving cars rely on deep learning for perception tasks, identifying pedestrians, reading traffic signs, and detecting lane boundaries to navigate safely. In healthcare, medical image diagnosis uses deep learning to detect tumors or abnormalities in MRI and CT scan, often achieving accuracy levels comparable to experienced radiologists. Generative AI is a branch of deep learning focused on creating new content. These models learn patterns from massive datasets, then generate entirely new data, including text, images, audio, and even video, that resembles what they have learned. For example, ChatGPT can produce human-like text responses, answering questions, writing articles, or drafting scripts. DALL-E and Midjourney can create realistic images from simple text prompts, turning ideas into visuals. In the music world, AI music generation can compose original songs in various styles. And in programming, tools like GitHub Copilot can assist developers by creating code snippets, suggesting completions, and even writing entire function. Artificial intelligence is no longer a futuristic concept reserved for research labs or tech giants. It has become a transformative force that touches nearly every profession, from healthcare and finance to manufacturing, education, and creative industries. For working professionals, AI is not just a tool, it is an enabler of smarter decisions, higher efficiency, and innovation at scale. Understanding AI's potential is essential to remain competitive in today's rapidly evolving job market. Artificial intelligence delivers value to professionals in three powerful ways. First, automating repetitive tasks. Routine time-consuming activities can now be delegated to AI-powered systems. For example, HR teams can use AI to screen resumes, accountants can process invoices automatically, and customer service teams can provide 24/7 support through AI chatbots. Second, enhancing decision making. AI provides data-driven insights that reduce guesswork and improve accuracy. Doctors can rely on AI-assisted diagnostic tools, financial analysts can predict market trends more precisely, and engineers can speed up product design using AI simulations. And third, unlocking innovation. AI enables the creation of new possibilities, products, and services. Designers can generate concept art with AI, marketers can personalize campaigns with AI-driven analytics, and researchers can accelerate discoveries with AI-assisted analysis. In short, AI is not just about efficiency. It is about smarter decisions, faster growth, and unlocking creativity at scale. One of the most powerful aspects of artificial intelligence is its domain agnostic nature. In simple terms, AI strength lies in its ability to learn patterns from data, no matter which industry it comes from. For example, in healthcare, AI can analyze medical scans. In retail, it can study customer purchase histories. In manufacturing, it can detect patterns in machine vibration logs. And in education, it can track student performance metrics. The same core principles of AI, learning from data, finding patterns, and making predictions, apply everywhere. That's why AI is not limited to one profession or one sector. It is truly universal. Ignoring artificial intelligence is no longer an option for professionals. Those who fail to adapt risk falling behind peers who are already leveraging AI tools. They may lose efficiency, lose competitiveness, and even miss out on opportunity for innovation. In contrast, professionals who embrace AI gain a strong advantage. They build career resilience in a tech-driven world. They learn how to collaborate effectively with AI systems, and they open doors to lead transformation projects in their fields. Simply put, AI will not replace professionals, but professionals who use AI will replace those who don't. Let us look at some real world case studies of AI across different domains. In healthcare, AI-assisted radiology helps doctors deliver faster and more accurate diagnosis. In finance, AI-powered fraud detection systems reduce financial losses by identifying suspicious activity in real time. In manufacturing, predictive maintenance powered by AI lowers downtime cost by detecting machine issues before they become failures. In marketing, AI enables smarter customer segmentation, which leads to higher campaign return on investment. In education, personalized learning platforms adapt to each student's progress, creating better engagement and outcomes. And in law, AI speed up document analysis, allowing legal professionals to prepare cases more efficiently. These examples show that AI is not limited to one industry. It is transforming every profession it touches. Here are the key takeaways for professionals when it comes to artificial intelligence. First, AI is a skill amplifier. It doesn't replace you, it enhances your abilities. Second, AI literacy is now a core competency, just like digital literacy was essential 20 years ago. AI literacy is a must-have skill today. And third, AI does not create users, it creates leaders. Those who truly understand AI will be the ones shaping how it is applied in their field. What is the bottom line? AI is not just the future, it is your competitive advantage today. Welcome to this presentation on evolution of artificial intelligence. AI has come a long way from simple rule-based systems to powerful tools that can create content, mimic human creativity, and handle complex tasks. This progress didn't happen overnight. It was built step by step through revolutions in how machines perceive, learn, and generate. In this journey, we'll explore four major areas of AI: symbolic AI, statistical AI, deep learning, and the exciting new frontier of generative AI. Each stage pushed the boundaries of what machines can do, and by understanding this evolution, we will be better prepared for the present and the future. Whether you are a developer, a researcher, or a decision maker, this knowledge gives you the context you need to make smarter choices with AI. So, let us begin with a quick overview of these four transformative stages. Artificial intelligence didn't appear overnight. It's the result of decades of progress in both ideas and technology. In this presentation, we'll look at AI's journey through four big eras, each one reshaping what machines can do. First came symbolic AI, where rules and logic were written directly into machines. Then statistical AI, using data and probability to make smarter predictions. Next, deep learning, where machines begin uncovering complex patterns from massive amounts of raw data. And today, we are in the era of generative AI, where machines are not only analytical but creative. Understanding this journey is not just theory. It helps professionals choose the right tools and models for the real challenges they face in their fields. So let us dive in, starting with the foundation, symbolic AI. Let us start our journey in the 1950s with the symbolic AI, the rule-based era. Back then, The belief was that intelligence could be built by manually encoding knowledge into machines. Programmers wrote logic step by step. If this happens, then do that. This approach was deeply inspired by formal logic and mathematics. Symbolic AI led to some of the earliest breakthroughs. For example, Mycin, an expert system for treating infections, could even outperform junior doctors in certain cases. Early chess programs also used handcrafted rules and decision trees to make their moves. These systems were clear and transparent, and they work well in very specific tasks. But they were also brittle. A small change in input could break the whole system, and updating them meant rewriting massive set of rules. Because of these limits, researchers began searching for more flexible and data-driven approaches. That shift brought us into the next era of AI, that is statistical AI. The 1980s brought a major shift in the AI, from symbolic reasoning to statistical learning. Instead of programming every rule by hand, engineers began building models that could learn patterns from data using probability and statistics. This era gave us practical systems like spam filters powered by nav bias and early speech recognition models using hidden Markov models. These approaches made AI more adaptable to real-world situations, even when the data was noisy, inconsistent, or incomplete. But challenges remained. Models required a lot of manual effort to engineer the right features, and the classic phrase applied: garbage in, garbage out. The quality of the results was tightly bound to the quality of the data. Still, this era built the foundation for next revolution in AI, that is deep learning. The 2010s marked the rise of deep learning, a turning point in AI powered by stronger computers and smarter neural network designs. Unlike earlier methods, deep learning models could automatically extract useful features straight from raw data. No heavy manual pre-processing is needed. So this era brought huge breakthroughs. Neural networks dominating image recognition, recurrent and transformer models driving advances in language translation, and deep architectures revolutionizing speech recognition. These systems proved that with enough data and compute, AI could reach and sometimes even suppress human level performance in specific tasks. But these were trade offs. Deep learning demanded massive datasets, enormous computing power, and the models often work like black boxes, difficult to explain and harder to fully trust. Still, this era set the stage for the next big leap in AI, that is generative intelligence. We have now reached the current frontier of AI, the era of generative models. Unlike earlier systems that only analyzed or classified data, generative AI can create new content. From human-like conversions to stunning digital art, these models extend and even mimic human creativity. This revolution is powered by transformer architectures and large-scale training. Tools like ChatGPT and GitHub Copilot are everywhere, helping people write, design, and code. They are not just boosting personal productivity, they are transforming entire industries. But with this power come new challenges. Generative AI can produce misleading content, amplify biases, and raise difficult ethical and legal questions. That's why adoption must go hand in hand with responsibility, transparency, and thoughtful design. Understanding the evolution of AI is not just theory, it is highly relevant for today's professionals. Each era of AI brought new strengths and new limits. By learning from them, we can choose the right tools and avoid repeating past mistakes. For example, symbolic AI taught us transparency, statistical AI introduced adaptability, deep learning gave us perceptual intelligence, and generative AI unlocked creative synthesis. These approaches are not interchangeable. Each has its strength and weakness depending on the problem you are solving. As generative tools become more common, it is important to use them statistically, not just reactively. Whether you work in business, healthcare, law, or creative arts, your understanding of AI journey will shape how well you can lead, innovate, and adapt. To wrap up this journey, we have seen how AI has grown from handcrafted rules to probabilistic models to powerful neural networks that can both perceive and now create. Each era expanded what machines could do, and each brought new opportunities along with new challenges. Today's AI is at a convergence point. It's not only generating text and images, but also being woven into fields like bioengineering, healthcare, and education. But with this power comes responsibility. The more capable our systems become, the more important it is to design them with ethics, accountability, and purpose. As professionals, we are not just users of AI, we are stewards of where it goes next. By understanding the past, we are better prepared to shape a future that is innovative, inclusive, and intelligent by design. AI is not just the future, it is already here transforming industries today. This presentation opens with a look at how different sectors are using AI driven by real practical use cases, not theory. In finance, where every millisecond counts, AI powers fraud detection and automate trades, delivering speed, precision, and risk control. In healthcare, AI enables rapid diagnosis and support personalized treatment planning. In retail, AI thrives on predictive personalization, helping business understand and serve customers better. And in manufacturing, AI drives intelligent automation, streamlining operations, and boosting efficiency. Across all these industries, the lesson is clear. While the data and code may differ, the power of AI lies in adapting common techniques to deliver measurable value. Let us explore each of these sectors more deeply. Finance is the one of the most advanced sectors when it comes to AI integration. The sheer volume and velocity of transactions make it a prime candidate for machine learning solutions that can process data in real time. Fraud detections has evolved from rigid rule-based systems to dynamic ML models that adapt to changing behaviors. Algorithmic trading now uses deep learning to spot and exploit patterns faster than human traders ever could. Meanwhile, AI enhances grade scoring by considering behavioral data, opening doors to wider financial inclusion. Customer service also benefits with AI-powered bots that understand intent and manage even complex workflows. So the result is banks are saving cost, reducing fraud, and delivering a smoother customer experience. AI's impact in healthcare is deeply human. By improving the speed and accuracy of diagnosis, AI empowers doctors to begin treatment sooner, especially in critical conditions like cancer. One standout case is medical imaging. Deep learning can scan images in minutes, catching signs that even experts might miss. Predictive analytics also play a big role, helping hospitals forecast high-risk cases and allocate resources more efficiently. Beyond diagnostics, AI is speeding up drug discovery by identifying promising candidates faster. And for patients, digital health assistants provide guidance and support right at their fingertips. The result is personalized, proactive care delivered at scale. In today's competitive retail world, the edge comes from personalization and precision, and AI makes both possible. Recommendation engines, driven by vast amount of customer data, deliver the right product at the right time and that dramatically boost sales. Forecasting tools help avoid both overstock and missed sales by optimizing inventory based on real demand. Dynamic pricing adds another layer, adjusting offers in real time to stay competitive. Even in physical stores, computer vision is transforming shopping from instant checkout to smart self alerts. The result is a faster, smarter, and more customer friendly retail experience. In manufacturing, AI delivers efficiency at scale. Predictive maintenance cuts down on unplanned downtime, directly improving output and reducing cost. By analyzing sensor data in real time, systems can anticipate failures and trigger repairs before they happen. On the quality side, computer vision spot product flaws with incredible speed and accuracy, making sure only the best product reach customers. In supply chain logistics, AI predicts optimization routes, keeping production lines running smoothly. And then there is robotics. Intelligent machines powered by AI now adapt to complex and changing tasks. The result is leaner operations, safer workplaces, and a strong bottom line. This matrix shows the cross-sector impact of AI. The tools may be the same: machine learning, computer vision, natural language processing, but their use looks very different depending on each industry needs. In finance, speed and accuracy matter most. In healthcare, it is all about reliability and life-saving precision. In retail, the focus is understanding customers in real time. And in manufacturing, the priority is operational consistency and safety. Despite these differences, one pattern is clear: AI delivers the most value when it is built into specific high impact processes. That is where the real return on AI investment comes to life. Artificial intelligence runs on mathematics, and at its heart lies linear algebra. But linear algebra is not just theory, it is the practical toolkit of AI. Vectors describe features like a snapshot of important details. Matrices perform transformation, shaping and manipulating data. And tensors capture the complexity of real world and high dimensional information. Once you grasp this essential, you will begin to understand how AI truly thinks at its mathematical core. In the coming slides, please let us discuss this more. A vector is simply a list of numbers, but it carries both size and direction. For example, in finance, a vector like 1200, 800, 500 could represent monthly spending on food, travel, and healthcare. In healthcare, 72, 120, 98.6 might capture a personal heart rate, blood pressure, and body temperature. Vectors are powerful because they capture the key features of an entity, making them the basic building blocks of machine learning. We can do simple yet useful operations with vectors. Addition. Let us combine features. The dot product measures similarity, which is useful in recommendation systems. And scaling allows us to amplify or shrink values. With tools like NumPy, these operations are easy to perform in just a few lines of code as shown here. A matrix is like a table of numbers arranged in rows and columns. It helps organize information and perform transformations. For example, in retail, a matrix can store product sales across different months. In computer vision, an image is just a matrix of pixel values. And in analytics, we often use a user item rating matrix to recommend products. Matrices are extremely important in AI because they power neural networks where inputs are multiplied by weight matrices to make predictions. Some key operations with matrices include transpose, which swaps rows and columns, multiply, which combines data and parameters. This is the core of machine learning. And inverse, which helps solve systems of equations. With tools like NumPy, these operations are easy to run in just a few lines of code as shown here. A tensor is like a big brother of vectors and matrices. While vectors are one-dimensional and matrices are two-dimensional, tensors extend into higher dimensions. For example, a color image is a 3D tensor with height, width, and RGB channels. When we process a batch of images in deep learning, that becomes a body tensor. And in healthcare, an MRI scan can be seen as a 3D tensor made of layer slices. Tensors allow AI models to handle large multidimensional data efficiently, making them the backbone of modern deep learning. With libraries like NumPy, we can easily create and work with tensors in just a few lines of code as shown here. Linear algebra is the backbone of artificial intelligence. It helps represent data, whether it is text, images, or audio, using tensors. It powers computation since neural networks are built from layers of matrix multiplications. It enables optimization using vector and matrix calculus to train models. And it provides scalability with GPUs accelerating massive matrix and tensor operations for deep learning. In short, the elegance of linear algebra transforms raw data into intelligent insights, making AI not just possible but more powerful. Let us see how linear algebra powers face recognition step by step. First, the input image is processed. It represented as tensor, capturing height, width, and color channels. Next, a neural network takes over. It uses matrix multiply and transformation to extract unique features from the face. These features are then stored as vector in a high dimensional space. Finally, when comparing two faces, The system measures similarity using dot product of their feature vectors. In simple terms, linear algebra transforms raw pixels into meaningful patterns, allowing AI to recognize faces with impressive accuracy. Artificial intelligence works in a world full of uncertainty. The data it gets is often incomplete, noisy, and even contradictory. But still, AI is expected to make smart and trustworthy decisions, predictions, and recommendations. This is why probability and statistics are so important. They give AI tools to deal with uncertainty and form the backbone of decision making. Ever wondered how AI predicts the future or even creates new content? The secret lies in probability. AI doesn't give guarantees, it works with chances. For example, a model might say there is a 78 chance a customer will leave. In reinforcement learning, probability helps AI balance between exploring new options and sticking with proven ones. And in generative AI, probability decide what word, pixel, or sound come next, powering everything from chatbots to image generators. That is why probability matters in AI. It is the engine that helps machine handle uncertainty and still make smart, reliable decisions. Let us break down some core probability concepts in simple terms. First, a random variable. This just means an uncertain outcome, like rolling a dice and getting a number between 1 and 6. Next, the probability distribution. It assigns chances to each possible outcome, helping us know what is more or less likely. Then we have expectation or mean. This is simply the average outcome if we repeat an event many times. Finally, variance and standard deviation. This measures how spread out or uncertain the outcomes are. Together, these ideas form the foundation of probability, and they are the tool AI uses to make sense of uncertainty in the real world. Bayes' theorem is a way to update our beliefs when you see new evidence. Think of it like this. We start with a prior belief called a PH, then we ask, if my belief were true, how likely is the evidence? That is the likelihood, P E bar H. We also consider the overall chance of evidence itself, that is PE. Finally, by combining all of these, we get the posterior PH by E, our updated belief after seeing the evidence. In short, prior belief, evidence, and then updated belief. This is how spam filters, medical tests, and even AI system keep learning and improving. Let us see how Bayes' theorem works with a spam filtering example. First, we start with our prior knowledge. 20% of emails are spam, and in those, 60% contain the word lottery. But in genuine emails, only about 1% contain lottery. Next, we get new evidence. An email arrives with the word lottery. When we calculate, the total probability of seeing this word is 0.128. Finally, we update our belief using Bayes' theorem. The chance that email is spam jumps to about 93.75%. This is the power of Bayes' theorem. It helps spam filters, medical tests, and even AI system make smarter decisions based on the evidence. Bayes' theorem is not just theory, it powers many real-world applications. First, naive Bayes is widely used in text classification, like detecting spam or analyzing sentiment in reviews. Next, Bayesian networks help us model complex cause and effect relationships, useful in medicine, troubleshooting, and decision making. And finally, Bayesian optimization is a powerful tool for tuning machine learning models, making them smarter and more accurate. So, bias is everywhere, from emails to AI, shaping smarter systems around us. Distributions are the shapes of data. They help us understand how information is spread out, and this is a key part of AI and machine learning. By looking at data distributions, we can model uncertainty, make better predictions, and find real insight in complex datasets. From simple yes or no decisions all the way to advanced neural network outputs, distributions guide how we read, understand, and use data. Let us look at discrete distributions, which are all about counting events. First, the Bernoulli distribution. This models a single yes or no trade, like whether someone clicks on ad or not. Next, the binomial distribution. This extends Bernoulli to many trades. For example, out of 10 people visiting a website, how many actually make a purchase? Finally, the Poisson distribution. This helps us model rare events over time or space, like the number of website crashes in a week or how many customer calls arrive each hour. Together, these distributions give us powerful tools to understand and predict real-world events in AI and machine learning. Let us talk about continuous distribution, the model that helps us understand real-world data. First, we have the normal distribution, also called bell curve. It is everywhere in nature, measurements, and even AI. Defined by mean and standard deviation, it is backbone for regression, PCA, and noise modeling. Next, the exponential distribution. This one models waiting times, like when next customer arrives or when a system fails. Because of its memoryless property, it is perfect for survival analysis and queuing theory. And finally, the uniform distribution. Here, every value in a range has equal probability. It is simple but powerful. It is widely used for random sampling and initializing weights in neural networks. Together, these distributions power statistical modeling, helping AI and data science make sense of continuous and real-world values. How do distribution power artificial intelligence? Let us break it down. First, Gaussian distribution. They drive regression models, PCA, and even noise modeling. Thanks to the central limit theorem, they are everywhere in AI. Next, Poisson distribution, perfect for anomaly detection. In cybersecurity and fraud detection, they spot unusual spikes or sudden drops in activity. Then comes softmax, a hero in neural networks. It converts raw output into probabilities, helping AI classify and measure uncertainty. And finally, generative models from GANs to VAS. They learn entire data distributions to create brand new, realistic samples like images, voices, or text. That is how distribution meet machine learning, turning raw math into real-world AI power. In AI, not every improvement is real. Sometimes it is just random noise. That is where hypothesis testing comes in. It helps us separate genuine progress from false signals, giving us confidence that our models truly work. As Edwards Deming once said, in God we trust, all others must be data. And in AI, data-driven decisions are everything. Let us make hypothesis testing super simple. It is just 5 steps. Step 1. Start with null hypothesis. Assume nothing is happening, no effect exists. Step 2. Define the alternative hypothesis. This is the effect you are hoping to prove. Step 3. Choose your test, like a t-test or ANOVA, depending on your data. Step 4. Compute p-value. This tells you how likely your results are if nothing was really going on. And step 5. Make your decision. If the p-value is small enough, you reject the null and say, yes, the effect is real. That's it. 5 simple steps to turn data into confident decisions. Here is how A/B testing works in real AI products. Step 1. Set up hypothesis. The null says old and new algorithms perform the same, while the alternative says the new one improves click-through rates. Step 2. Run the experiment. Show different users different algorithms and collect click data over time. Step 3. Analyze results. If the p-value is small, like here 0.03, it means the improvement is statistically significant. Step 4. Deploy the decision. With confidence, roll out the new algorithm to everyone because the gain is real, not random chance. That is A/B testing, turning data into smarter AI decisions. Hypothesis testing is not just theory, it powers real AI applications. First, model validation. It checks if your new model truly beats the baseline, so you don't deploy something that only looks better by chance. Second, feature important testing. It tells us which features genuinely impact performance and which ones are just noise. This is the key for feature selection and making models interpretable. And third, A/B product experiments. From recommendation systems to AI changes, A/B testing ensures that improvements are real and statistically significant before a full rollout. This is how hypothesis testing keeps AI reliable, trustworthy, and effective in real world. Three powerful ideas drive modern AI. First, Bayes' theorem. It updates beliefs with new evidence, powering probabilistic reasoning and machine learning. Second, distributions. They capture uncertainty in data, helping us model and predict real-world behavior. And third, hypothesis testing. It separates true effects from random noise, giving us confidence in our decisions. And these are not just abstract math, they are behind fraud detection, medical diagnosis, recommendation systems, and even the predictive text you use every day. Optimization is the heart of artificial intelligence and machine learning. Every AI model, whether it is linear regression or deep neural networks, learns through optimization. But what does that mean? At its core, optimization is just about improving performance, reducing errors, or increasing the accuracy. Think of it like finding the lowest valley in a mountain landscape. Gradient descent is the path we follow step by step to reach that valley. In this video, let us explore the basics of optimization and see the difference between convex problems, where there is one clear valley, and non-convex problem, where there are many hills and valleys, making the journey more challenging. So, what is optimization in AI? Think of it like fine-tuning machine until it works at its best. First, the definition. Optimization means adjusting the model parameters, its weights and biases, so the prediction match reality as close as possible. Next, the objective function, also called the loss or cost function. This is just a formula that measures how far off the predictions are. For example, mean square error is often used in regression. Finally, the goal. We want to find parameter values that minimize this loss. You can imagine it as searching for the lowest value in a big landscape of errors. Gradient descent is called the workhorse of AI, and here is why. Imagine you're standing on a foggy mountain trying to reach the valley below. You can't see the whole landscape, but you can feel the slope under your feet. If you keep stepping downhill, adjusting your step size, you will eventually reach a low point. That is exactly how gradient descent works. It helps model minimize errors step by step. Mathematically, it updates parameter using the gradient of loss function, moving closer to best solution each time. Now, there are three popular types. Batch gradient descent, stable but slow, since it uses the entire dataset at once. Stochastic gradient descent, faster but a bit noisy, since it updates with just one sample at a time. Mini batch gradient descent, the most common in deep learning, striking the right balance between speed and accuracy. This is why gradient descent powers almost every AI model that you use today. Let us look at convex versus non-convex problem. First, convex problems. Imagine a smooth bowl. There is only one lowest point called the global minimum. That means optimization is easy, so you'll find always the best solution. An example is linear regression, where the error is measured using mean squared error. Now, non-convex problems. These are trickier. The curve has many valleys and peaks. You might get stuck in a small dip called a local minimum instead of finding absolute best point. This is common in deep neural networks with millions of parameters. That's why optimization in AI is challenging. Convex problems are straightforward, but non-convex problems make learning much harder. Optimization in AI is powerful, but it comes with challenges. Let us look at three big ones. First, the learning rate dilemma. If the learning rate is too high, the model overshoots the best solution. If that is low, training becomes painfully slow. So what is the solution? Use learning rate schedules and adapt to optimizers like ADAM or RMSPROB. Second, local minimum saddle point. Deep networks often use settle in a good enough spots rather than the perfect one. But good news is, in large models, many local minima are almost as good as global ones. Third, gradient vanishing or exploding problem. Sometimes gradients shrink too small or blow up too big during training. What is the fix? Use proper initialization, normalization, layers, active functions like ReLU, and techniques such as grading clipping. These solutions make training deep models much more stable and reliable. Let us connect optimization to real-world examples. First, a convex problem. Imagine allocating budget to just one ad channel. As you spend more, you get diminishing returns. It's like a smooth valley with one clear best point, which is easy to solve. Now, a non-convex problem. Think about trying a recommendation system like Netflix or Amazon. Here, many factors come into play: user preferences, context, and even seasonality. The optimization landscape has multiple valleys and peaks, making it much more complex. That's why convex problems are simple, but non-convex ones mirror the real challenges we face in AI today. Optimization is the engine that makes AI work. First, model training. Every single update in neural network, every weight and bias is powered by optimization. Second, efficiency. Optimization decide whether your model train in few hours or take several days. Third, accuracy. With right optimization, models avoid underfitting and overfitting, giving better predictions. And finally, scalability. Without efficient optimization, deep learning breakthroughs like today large model would never be possible. That's why optimization is the heart of artificial intelligence. In this video, let us explore the three most powerful tools every AI professional must know: NumPy, Pandas, and Matplotlib. NumPy gives you super fast math with arrays. Pandas helps you clean, analyze, and manage the data with ease. And Matplotlib allows you to bring your data to life with clear and colorful charts. Together, these libraries form the backbone of AI programming. Let us dive in and see how they make AI smarter and easier. Why is Python the language of choice for AI? It is simple, clean, and easy to read, but the real power comes from its ecosystem of libraries. NumPy gives you the speed and power for scientific computing. Pandas helps you organize and analyze data with ease. And Matplotlib allows you to turn raw numbers into clear and meaningful visuals. Together, these tools form the backbone of AI workflows, helping us pre-process data, build models, and visualize results. Let us talk about NumPy, the engine behind numerical computing in Python. AI models need fast operations like dot products, transposes, and matrix multiplication. Back propagation and gradient descent also depend on efficient computation. That is why NumPy is so important. with features like vectorization to speed up calculation, broadcasting to handle arrays of different shapes, and linear algebra tools like SVD. NumPy makes heavy math simple and fast. In short, NumPy is the backbone that powers AI computations. Now let us talk about Pandas, the ultimate tool for working with data in Python. Raw data is often messy, full of missing values, duplicates, and outliers. Pandas make it easy to clean and prepare the data. You can quickly filter and query to get only the information you need. It allows you to match multiple datasets together and analyze patterns using powerful group and aggregation methods. In short, Pandas turn raw data into insights, making it one of the most important tools in every AI workflow. Finally, let us look at Matplotlib, the library that helps us see and understand data. In AI, visuals are critical. With Matplotlib, we can easily spot trends, outliers, and patterns before training models. We can also track model performance and explain results clearly to others. It supports all types of plots, line bar, scatter, histogram with custom titles, labels, and seamless integration with NumPy and Pandas. In short, Matplotlib turns raw numbers into clear insights, making data visualization a powerful step in every AI workflow. So, how do these libraries work together in AI workflows? First, we use Pandas to load and explore data from CSV, SQL, or other sources. Next, the clean data is converted into NumPy arrays for fast and efficient processing. Then, machine learning models are trained using frameworks like TensorFlow or PyTorch, both of which rely on NumPy under the hood. Finally, we use Matplotlib to visualize results, spot insight, and communicate findings. Together, they form a seamless pipeline powering almost every AI project. Behind every powerful AI model, there is a hidden hero, that is data pipeline. Think of it as a factory assembly line where raw messy data is collected, cleaned, and labeled before it finally powers intelligent machines. First, we collect data from apps, sensors, images, videos, and endless stream of online activity. Without collection, there is no AI. Next, we clean the data. Why? Because raw data is messy. Missing values, duplicates, errors. If we don't fix them, the AI will fail. Clean data is the secret sauce of accurate predictions. Finally, we label the data. A photo tagged as a cat or dog, or an X-ray labeled healthy or disease. These labels are the teacher that trains AI to understand the world. So remember, great AI does not start with fancy algorithms. It starts with a strong data pipeline. Because in AI, garbage in means garbage out. Stay tuned because in the next slide, we will break down each step with a real world examples from self-driving cars to healthcare and e-commerce. Why data pipelines matter so much in AI? Because without them, even the smartest algorithms are useless. A data pipeline is like a factory assembly line. Raw messy data goes in, and step by step it is refined into high quality fuel for AI. First, it ensures data quality, accuracy, consistency, and reliability. No more messy, broken data ruining your models. Second, it provides scalability. Imagine handling millions of records at lightning speed. That is the power of pipeline. Third, it maintains traceability. Every step leaves an audit trail, so compliance, debugging, and accountability become easy. And finally, it supports reproducibility. You can retrain your models anytime with same inputs and get the same trusted results. That's why data pipelines are the hidden backbone of AI success. Without them, it is garbage in, garbage out. The very first step in building AI data is data collection, because without data, there is no intelligence. AI applications thrive on three kinds of data: structured data like databases, spreadsheets, and purchase logs; unstructured data like text, images, audio, and videos from social media or medical scans; and streaming data, real-time feeds from sensors, stock markets, or even your smart home devices. But here is the secret: collecting data is not about hoarding everything, it is about collecting what is truly relevant. What are best practices? Use APIs and web scraping for automation, IoT devices for real-time analytics, and crowdsourcing platforms for labeled datasets. About biggest challenge: ensuring privacy, following rules like GDPR and HIPAA, and avoiding biased sampling, because biased data means biased AI. So, great AI begins with smart data collection, the right data from the right sources with the right ethics. Raw data is messy, and if you don't clean it, AI will fail. Think about it: missing values in surveys, inconsistent formats like US, USA, United States, sensor glitches creating errors, duplicate entries for same customer, or even extreme outliers like $1 million transaction in retail log. That's why data cleaning is so critical. It transforms chaos into clarity. We fix missing data with imputation, standardize formats and units, remove duplicates, detect outliers using statistics, and normalize everything so models can learn rightly. Here is the catch: data cleaning is not glamorous, but it takes up nearly 60 to 80% of data scientist time. And yet, it is the backbone of trustworthy AI. Without it, even the most advanced models collapse. So remember, in AI, the magic don't start with algorithms. It starts with clean, reliable data. AI doesn't just learn from data, it learns from labeled data. Labels are the teacher that guide AI to make sense of the world. Think about it: a photo tagged as cat or dog, a sentence marked as positive or negative, or an X-ray labeled abnormal or normal. Without these labels, AI is just guessing in the dark. There are three ways we label data. First, manual annotation. Human experts or crowdsourced workers tagging examples. Semi-automated labeling, where machine pre-label and humans verify. And third, programmatic labeling using rules, heuristic, or weak supervision tools like Snarkel. But here is the catch: labeling is hard, it is expensive, time consuming, and can even introduce biases if annotators make mistakes or bring cultural assumptions into the task. That's why the best practice is clear guidelines, multiple annotators for cross-checking, and continuous validation against real-world results. Remember this: the accuracy of your AI is only as strong as quality of your labels. Garbage level mean garbage intelligence. Now let us put all together. The data pipeline is not a straight line, it is a cycle of continuous improvement. It starts with collection, gathering data from structure sources like databases, unstructured sources like images or text, and even real-time streams from sensors. Next comes to cleaning, fixing errors, removing duplicates, and standardizing everything so the data is reliable. Then we move to labeling, adding meaning through annotations, the step that teaches AI what data really represents. Finally, we get the output, a high quality dataset, polished and ready to train powerful AI models. But here is the key, this process loops back. Every time errors or gaps are found, the pipeline feedbacks into collection or cleaning. That is how AI gets smarter, stronger and more accurate over time. So how does a data pipeline work in real world? Let us look at three powerful examples. First, self-driving cars. Cameras and LiDAR collect endless streams of images. The raw data is cleaned to remove sensor noise and then label pedestrians, lanes, traffic signs. Without this pipeline, autonomous cars could even stay on the road. Second, healthcare diagnostics. MRI scans are collected, noisy scans are removed, and radiologists label conditions like normal or abnormal. This pipeline turns images into life-saving insights. And third, e-commerce recommendation systems. Every click, every purchase, every scroll is collected. Duplicate or bot clicks are cleaned out and data is labeled as browsing versus buying. That is how AI learns what you are likely to buy next. From cars to hospitals to online shopping, the data pipeline is the invisible engine making AI practical, powerful, and real. AI has two big moments in its life, training and inference. Think of training like going to school. The AI is learning from tons of examples, making mistakes, and improving. Inference is AI uses what it learned to give you real answers in the real world. Training builds the knowledge, inference applies it. Together, they make AI powerful, smart, and useful for everything we do today. Training is how an AI learns to think. The model looks at millions of examples, finds patterns, and corrects itself again and again until it gets smarter. Think of it like a student practicing problems. Make a guess, check the answer, fix mistakes, and repeat this cycle millions of times. But training needs use power, advanced GPUs or TPUs, and it can take hours, days, or even weeks. This hard work is what gives AI the knowledge it uses later in the real world. Training AI is not easy, it is heavy lifting. It needs huge amounts of data, often terabytes of examples. It costs thousands of dollars in storage, energy, and hardware, and it runs 24/7, sometimes for days or even weeks. For example, to teach AI the difference between cats and dogs, you don't just show a few pictures, you show it millions. This massive effort is what gives AI its superpower to recognize, predict, and perform. Inference is where AI comes alive in the real world. After all the hard training, this is the moment AI shows what it has learned. You give it new input like uploading a photo and instantly it applies its knowledge to give you the answer. It is fast, accurate, and often in just milliseconds. For example, train an AI to recognize cats and dogs. The next time you upload a picture of cat, it immediately tells you this is a cat. That is inference, AI in action, right at your fingertips. Training and inference may sound similar, but they are totally different. Training is the heavy work. The AI learns pattern from massive datasets using powerful GPU. It takes hours, days, or even weeks, and it costs a lot. Inference is the payoff. The AI applies what it learned to new data. It runs light, often on your phone or laptop, and gives results in just milliseconds. In short, training is the brain building phase. Inference is the action phase, which is fast, smart, and ready for real world use. Here is a real world example. You know well, voice assistants like Alexa, Siri, or Google Assistant. During training, the AI learns from thousands of hours of speech recordings. It listens to different accents, languages, background noises, and speech patterns, so it can understand human voice in all situations. Then comes inference, the part you use every day. You say, play music, and instantly the assistant understands your intent, process your voice in real time, and execute the command within seconds. That is the power of training and inference working together to make AI feel smart and natural in our daily lives. Fraud detection is one of the smartest uses of AI. In the training phase, the system learns from years of bank transactions, both safe and fraudulent, and builds patterns of suspicious behavior. Then in real life, when you swipe your card, the system instantly checks the transaction against those patterns, and within milliseconds it decides approve it or flag it as suspicious. That is AI in action, protecting your money every single day. Healthcare is where AI truly saves lives. In the training phase, AI studies millions of X-rays labeled by expert doctors. It learns to recognize even tiniest patterns that may point to diseases. Then comes to inference phase. A new X-ray is uploaded, and within seconds, the AI highlights possible issues. This helps doctors make faster and more accurate diagnosis, giving patients a better chance at early treatment and recovery. That is the life-saving power of AI in healthcare. Why does the difference between training and inference matter? For developers, it guides where to focus, improving training for better accuracy or speeding up inference for faster results. For business leaders, training is a big investment, but inference is where customers feel the real value and revenue is generated. And for AI products, success depends on balance, strong training to build accuracy, and efficient inference to keep users happy and engaged. That's why this distinction is not just technical, it is critical for future of AI. Training builds the brain, inference uses the brain. Without training, AI can't learn. Without inference, AI is useless to people. Both pages are essential. Training creates the foundation of knowledge, while inference delivers real value in the real world. Think of it this way. Training is like studying hard to gain knowledge. Inference is applying that knowledge when it really matters. Together, they make AI smart, useful, and impactful. Artificial intelligence may sound complex, but it all begins with a few simple ideas. In this video, we'll uncover the key concepts that power every AI and machine learning system called features, labels, epochs, overfitting, and underfitting. Think of features as the clues, labels as the answer, epochs as the practice round, and overfitting and underfitting as the mistakes models make when they don't just learn the right. By the end, you'll see how these building blocks connect raw data to real intelligence. So stay tuned because understanding these concepts is the first step to mastering AI. Let us start with most important building block of AI called features. Features are input variables, the signals that describe your data. Think of them as the ingredients in a recipe. Better ingredients make a better dish, and in AI, better features make a better model. For example, when predicting house prices, features can be the number of bedrooms, square footage, or location. In images, features are pixel values, colors, edges, or textures, things that help classify what is inside a picture. And here is the golden rule: choosing the right features often matters more than algorithm itself. This is why feature engineering is one of the most powerful skills in AI. Now that we know features are the inputs, let us talk about labels, the outputs. Labels are what we want the model to predict. If feature are the ingredients, labels are the final dish we are aiming to cook. For example, in spam detection, the label is either spam or not spam. In stock forecasting, the label is tomorrow's stock price. And in healthcare, the label could be disease or healthy. Simply put, features are what we know, labels are what we want to know, and together they form the question and answer field that makes AI smart. AI doesn't learn everything in one go. It learns through repetition. An epoch is one complete pass through the entire dataset. But one pass is never enough. That's why we train models over multiple epochs, allowing them to slowly adjust and discover patterns. For example, with 10,000 training samples over pi echoes, the model actually sees every sample 5 times, getting better with each round. But here is the catch. Too few epochs and the model doesn't learn enough, that is underfitting. Too many epochs and it memorizes the data, that is overfitting. The secret to powerful AI is finding that sweet spot in between. Overfitting happens when an AI model learns too much. It doesn't just learn the real pattern, it also memorizes noise and random details from the training data. As a result, it performs great on practice data but fails when faced with new data. Think of it like a student who memorizes answers without understanding concepts. They score high on practice tests but fail in real exams. That is overfitting, knowing the answers by heart but not truly understanding the subject. How do we recognize overfitting? It shows up as very high accuracy on training data but poor accuracy on test or real world data. In short, the model has memorized instead of learned. So, what causes it? Models that are too complex, training for too many epochs, or skipping regularization techniques. And here is how to fix it. Use regularization like L1, L2, or dropout. Add more diverse training data. Or stop training early when validation error starts rising. The goal is simple: train a model that doesn't just ace the practice test but performs well in the real world. Underfitting happens when a model is too simple to capture the real patterns in the data. It's like a student who barely studies and give generic answers, failing both practice and real exams. The telltale sign of underfitting is low accuracy, not just on test data, but also on training data. In short, the model has not learned enough to make sense of the data. Underfitting happens when the model is too weak to capture the real patterns in the data. There are three big reasons why this happens. The model is too simple, for example, using linear regression on highly complex data. The model has not been trained enough. 2p epochs mean it didn't get enough practice. Or the features are poor, irrelevant, or missing inputs stop the model from learning properly. So how do we solve it? Use a more complex model, train longer with more epochs, and most importantly, improve feature engineering by adding the right data with domain knowledge. That is how you turn an underperforming model into a smarter one. Now let us put everything together with a real world example predicting customer purchases. First, we look at the features, things we already know about a customer like age, income, and browsing history. Next comes model training. The model goes through multiple epochs, learning patterns while avoiding the traps of overfitting and underfitting. Finally, we predict the label. Will the customer buy the product? Yes or no? And here is the golden rule. Balance is key. Train long enough to capture real patterns, but not so long that the model memorizes specific customers instead of general buying power. This balance is what makes AI predictions powerful and useful in the real world. To truly unlock your AI potential, you need to master the fundamentals. These 5 concepts, features, labels, epochs, overfitting, and underfitting are the foundation of every AI system. They give you the knowledge to understand why models behave the way they do. They give you the language to speak about AI with confidence. And most importantly, they give you the power to build AI solutions that deliver real results. Remember, master the basics and you will be ready to shape the future of AI. Artificial intelligence is moving faster than ever, but behind the magic of smart AI models, there are powerful tools and frameworks that make everything possible. Think of them as the toolbox for AI engineers, helping us build, train, and deploy models quickly and efficiently. In this section, let us explore 3 of the most powerful ones. PyTorch, which is loved for its flexibility and research-friendly design. TensorFlow, which is known for large-scale deployments and production-ready solutions. And Hugging Face, which is for pre-trained models and natural language processing. These tools are what turn AI ideas into real-world applications, powering everything from chatbots to self-driving cars. So let us unlock the future of AI with PyTorch, TensorFlow, and Hugging Face. Let us talk about PyTorch, one of the most powerful deep learning frameworks today, which is built by Facebook AI Research Lab. What makes PyTorch special? It is known for its flexibility, simplicity, and Python-friendly design. What are the key features? It uses dynamic computation graphs, meaning you can build and debug models on the go. It has strong community support with tons of tutorials, pre-trained models, and contributors from developers worldwide. With TorchScript, you can take your research models and make them production ready, running smoothly on servers, mobile devices, or even embedded systems. And thanks to GPU acceleration, it delivers high performance training with CUDA integration. What are the use cases? PyTorch shining cutting edge research like NLP and computer vision, rapid prototyping of AI models, and even powering real world systems like recommendation engine and fraud detection. So think of PyTorch as the researcher choice, perfect for experimenting with new ideas while still strong enough for large-scale deployment. Now, let us talk about TensorFlow, one of the earliest and most powerful deep learning framework developed by Google Brain. TensorFlow is famous for its production-grade scalability and a massive ecosystem of tools. What are the key features? It supports both static and dynamic graphs, giving flexibility and performance. With TensorFlow extended, you get a complete production pipeline for training, saving, and monitoring AI models. TensorFlow Lite brings AI to your phone and edge devices. TensorFlow.js lets you run AI models directly in your web browser. And with Google Cloud AI integration, deploying enterprise scale AI is seamless. What are the use cases? TensorFlow powers Google Search, YouTube recommendations, cloud native AI, and large scale deployment across web, mobile, and IoT. So think of TensorFlow as the enterprise powerhouse, perfect for companies that need scalable, production ready AI systems. Finally, let us look at Hugging Face, the platform that has truly transformed the AI world. Hugging Face is famous for making state-of-the-art AI model accessible to everyone. What started with transformation library has now grown into full AI ecosystems. What are the key features? The transform library gives you thousands of pre-trained models for text, images, audio, and more. The Model Hub is a massive community where developers share and reuse models. With Datasets library, you can quickly test and train AI ideas. The Inference API and Spaces let you run model instantly in the cloud or even build AI apps without heavy coding. And it works seamlessly with PyTorch and TensorFlow. What are the use cases? Hugging Face powers chatbots, sentiment analysis, translation, summarization, and even generative AI like text to image or audio. Think of Hugging Face as the AI democratizer, putting powerful AI tools into hands of everyone, not just big tech companies. Now, let us compare the three big names in AI framework: PyTorch, TensorFlow, and Hugging Face. PyTorch is easy to use, works with dynamic graphs, and is loved by researchers. It is best for research, prototyping, and flexible projects. TensorFlow is the enterprise powerhouse. It is scalable, production grade, and works great for large scale systems and enterprise AI solutions. Hugging Face is a community favorite with pre-trained models and easy access. It is perfect for NLP, generative AI, and rapid deployment. To sum it up, PyTorch shine in research and innovation. TensorFlow rules enterprise deployment, and Hugging Face makes AI accessible to everyone. So each tool has its strength, so the best choice depends on your AI journey. Here are key takeaways when choosing your AI framework. PyTorch gives you flexibility for research. It is best for innovation, experimentation, and pushing AI boundaries with dynamic computation graphs. TensorFlow shines in scalability and production. With a strong ecosystem, it is the go-to choice for enterprise-grade deployment and large-scale AI applications. Hugging Face is all about accessibility and pre-trained AI. It is perfect for NLP and democratizing AI, making powerful tools available to everyone through its massive model hub. In short, choose PyTorch for research flexibility, TensorFlow for production scalability, and Hugging Face for rapid deployments and easy access. Remember, Many teams actually use more than one framework at different stages. So the best choice depends on your project goals.